Okay, what is a simple harmonic motion? See, this is a pendulum. This is a simple harmonic motion. Now this is a spring. Now if I pull this, I'm just doing a tiny, and if I release it, this is also a simple harmonic motion. See, the motion is going to and fro about some mean position. But I must tell you that not all oscillatory motions are simple harmonic. There is a condition. Now let me go few examples which are not simple harmonic. Suppose oscillatory, but not SHM. Let me give you the example. I'll explain why it is so. Suppose you have a carom board and this carom board is perfectly smooth. Suppose mu is equal to 0 and the gravity is acting perpendicular to the board. It's horizontal, but I have drawn it vertically. Never mind. So these are the pockets of the carom board. Now suppose you have a line here. Now if you strike, or if you straight push your striker in the vertical direction, it goes this way, gets reflected on this beat, then comes back, it gets reflected on this beat, comes back, so it moves in a to and fro motion, right? But I tell you, this is not SHM, so this is not SHM. This is oscillatory, definitely this is oscillatory motion, but this is not SHM. Pendulum is SHM. This spring pendulum is SHM. Another very common example, suppose if you have a water full of beaker partially filled, and if you allow a small wooden block to float, and if you just push it and release it, this moves up and down. This is a simple harmonic motion. Now if you take also a U-tube like this filled with water, and if you press the water on one side and if you release it, this water goes up and down in a motion which is simple harmonic. I tell you again, this is not simple harmonic. So why this is not simple harmonic and why this is simple harmonic? Let me handle it a little bit without mathematics, then we will come into the detailed structure of simple harmonic motion. Now suppose if I oscillate a little bit. So this is how you oscillate. You shouldn't push, you just release it so that it moves in a plane. So moves in a plane means this string should remain in a Euclidean plane. See, if you watch it a little carefully, the velocity of this bob as it goes to the end decreases and stops, means it gradually decreases and stops. It doesn't decrease linearly. There is an equation that's a different issue. I'll come to that. But this velocity decreases slowly and stops, and it maximizes when it is at the mean position, right? This is the point where the velocity is maximum, and again it stops at this end. So this is the amplitude of oscillation. Same here. If you release it, if you watch it a little carefully, if you take a video of this and if you play it slowly, you will find that the velocity of this any point, suppose this point, it will gradually slow down and it will be 0 at the end. Also at the end means at the top, also at the bottom, and at the mean position, where mean positions means when it is not oscillating. Mean positions means what? Mean positions means when I have just kept it like this. This is the mean position. This is the point where the velocity will be maximum. But in case of this carom board, the velocity of this striker will be constant throughout. There is no force that pulls its back, that pulls the striker back. There is no restoring force. What happens is it just gets reflected here and it gets reflected here. If you plot the velocity time graph, so this is the velocity time graph, right? So velocity is constant, it's positive, it is moving in this direction. Once it immediately gets reflected, and it's like this. Then it's like this, right? It's a square square function. But in case of simple harmonic motion, it will be a sinusoidal curve or a cosinusoidal curve. Why it is sinusoidal, why it is cosinusoidal, I'll come to that. But try to realize this, that this is not simple harmonic. Okay. Now, what is a simple harmonic motion? What is the underlying mathematical structure? So let's analyze that first. So if I draw a circle, suppose this is a circle, and let me take a point P. Suppose this is a point P, and this point P is moving in a constant angular velocity. It's expected that you have already done circular motion. So this is theta, and if you have taken that this is the starting position t equals to 0, then theta will be omega times t, because this is the point. It had traversed for a time t. Now, what I am interested in is in the projection. What I am interested in is in the projection of this point P. So let's take a horizontal projection first. Okay. Now this is the projection, right? Now basically this projection, this point is this ball. Now, if this point P comes here, P, then projection comes here, so bob comes here. Again, if this projection is here, the bob comes here. If this projection is here, the bob comes here. This bob is actually a projection of a particle moving in a circle with constant angular velocity. Got it? Now let's suppose this point is xy. Okay, this point is xy. Now this is x. So what is x? X equals to, now if this radius of this circle is a, and what is the radius? Try to understand. The bob moves from here to here, right? Bob moves from here to here. So if you take this ball and if you release it, this is basically 2a, right? So from one end to the other, if you consider you should consider this length of this if you consider this path as straight, and if you should take this long enough, or you should make a very small angle. We say it's less than 4 degrees, but the smaller you take, the approximation will be better. That means this bob will move in a straight line. Anyway, so this is x equals to a. So a cosine of theta, and theta is omega t, right? And what is y? Suppose this is y projection. We'll leave it y, sine of omega t. Why we are taking the y projection? See, we are also interested in the vertical projection. How? Because for this fellow is moving in a vertical direction, right? So I have drawn the circle bigger to make you explain. But the thing is, this up and down motion is basically the motion of this y, this projection. Okay. So x equals to a cos omega t, y equals to a sin omega t. So this is for the pendulum, right? Sorry, this is for the this is for the pendulum, and this is for the spring. Okay, this is for the spring. Let's analyze the pendulum first. Now, if you take x equals to a cos omega t. Now, let's do it here. Let's do it here. X equals to, I must move this because I'm interested in the oscillatory motions, SHMs. So x equals to a cos omega t. So what is dx dt? A omega sin omega t, right? A negative sign comes out. Now what is this? This is v of x. That's the velocity of this ball. Now, if you do a little more mathematics, you will find it like this. That is minus a omega 1 minus cos square omega t, right, to the power of half. So that is because 1 minus cos square omega t is sin square omega t. Sin square omega t root is this thing, sin omega t. So minus a omega. What is cos square omega t? So that is, from here you can easily find cos omega t is x over a, right? So a omega 1 minus x square by a square to the power of half. Okay, so the velocity is in this direction, right? In this direction. It's going like this. It's negative x. Now let's differentiate another time. So what is the acceleration? So acceleration. So a of x. So that is d2 x dt2. So that is minus a omega. Then if you omega squared, because another omega comes, minus cos of omega t. So right. So what is a cos omega t? So that's x. So minus omega square x. Clear? Now this is the fundamental condition for SHM. So what is Ax? You can easily write that Ax is force along the x direction by mass. So that is minus omega squared x, right? So if then this implies Fx equals to m omega minus m omega squared x. Now this is the proportionality condition. This negative sign should be there, and if this force, this is called the restoring force. This is called the restoring force. Restoring force. This restoring force should be proportional to the displacement. In case of carom there is no restoring force. What happens is it gets reflected and it comes in this direction. So there is no restoring force within. So the shape is square shape, right? But in case of this pendulum, so this is cosine omega t. Now let's go into the value of this restoring force. Let's analyze it for this pendulum. So we have this bob here. Now this is mg. Now this is theta. Okay. Now if this is theta, so this is also theta. So this force is actually the restoring force. So what is this? This is mg. If this is theta, then mg cosine theta, and this is mg sine theta. Now I told you what is the condition. Condition should be theta is very small. So if for small theta, for small theta, sin theta is approximately theta. Huh? And which is actually, suppose this is, you will consider this as a straight line, and then if this length of the pendulum is L and this displacement is x, so what is theta? So theta is x over L, right? So that we know, x equals to r theta. So if we plug in the value, so what is the restoring force? Restoring force is mg sin theta. Now the moment you plug in x, so x is positive in this direction but the force is in the opposite direction. So mg, so you must place a negative sign minus x by L, right? So this is fx. So this is minus mg by L. This is x. This is fx, right? So this is the restoring force, and the restoring force is proportional to x. If the restoring force is proportional to x, you get the condition for SHM. Now you can easily find omega. So how will you find omega? So what is ax? So that is fx by m. What is? So that is minus g by L times x. Okay. So what is omega square? Omega square is g by L, and this implies omega is root over of g by L. Now what is this omega? This omega is the angular velocity of this particle whose projection I am interested in. Okay, and this projection is actually the SHM. So what is the time period? T equals to 2 pi by omega. Okay, and so that is twice pi root over of L by g. So this is the time period of SHM, and this is the condition for SHM. Now if you go into the vertical oscillation, so let's go to the vertical oscillation a little bit. So the vertical oscillations means you should take this part, y part, y equals to a sin omega t, and this y equals to, let's erase this part, y equals to a sin omega t. So what is y? So y is the vertical displacement. So what is Vy? Vy is a omega cos omega t. See, this is positive because if this particle goes like this, y increases, velocity is also in this direction, and if this particle goes like this, x decreases, velocity is in the opposite direction, so it's negative. It's very simple, mathematically it's absolutely clear. So again, from here you can easily find that sin omega t is what? Sin omega t is y over a. So that is y over a. Now what is Vy? So that's a omega 1 minus sin square omega t to the power of half. So that is a omega 1 minus y square by a square. So that is the velocity in the y direction. Now let's find ay. Ay is the acceleration, that is d2y dt2 or dvy dt, right? Very similar, means vy is what? dy dt, right? And what is ay? It's a dvy dt, that means d2y dt. So if you should differentiate it again, so a omega square sin square omega t, a negative sign comes because this is cos. Now what is sin omega t? What is a sin omega t? So that's y. So that's minus omega square y. See again, the acceleration will be proportional to y. Okay. So what is Fy? Fy should be may, right? So that is minus m omega square y. So again, the restoring force is proportional to the y displacement. In case of this thing, if you just release it like this, what is the restoring force? Suppose you have the spring here, okay, you have the spring here. Now when the spring is not, I mean to say when the spring is not oscillating, so this is mg, and suppose see, if you release it like this, so there is no weight, I consider this as weightless, this S also weightless, I consider it. Now if I release it, it elongates, right? It elongates a little bit L. So mg, so that means the weight of this thing is m. So mg must be equal to k times L. What is k? So that's the spring constant of this spring. So mg equals to kl. Now if I push it like this or I elongate it like this anyway, so it comes to another position. So it elongates a little bit more. So this x. Oh sorry, this should be y. This is y. Let me erase it and write it again. Let me so this is y. Okay. So now the restoring force is restoring force will be k L plus y. In which direction? In the opposite direction, right? So y is in this direction, it's decreasing, it's negative, but the force is in the opposite direction. But what should you do? You should, this is the force in which direction? In this direction. But what shall you do? You should take out the force already due to the mass. So that means mg. You should take it out. So that's the restoring force, right? So that's the restoring force. Okay. So that's force. But what I should tell you is, the moment you write Fy, you should place a negative sign. Why? Because if here y is positive, so that means if this goes up, the restoring force is in this direction, downward. If this goes down, the restoring force is in the upward direction. So it's just the opposite. So minus k L plus ky minus mg. Now say this mg is equal to kl, so these two gets cancelled. So Fy is equals to minus ky. Okay. Again, what's the acceleration Ay? See again, let me say the condition. So this is the condition for SHM. What is the condition? Force is proportional to y, right? Force is proportional to the displacement, and what is acceleration? Y. So that is minus k over m. So that's mass times y. Okay. So that's mass times y. Now, so that must be. We should compare this ay with minus omega square y. So what is omega square? Omega square is k over m, right? So t is equals to 2 pi by omega over m by k. So that is the time period for the SHM in case of spring pendulum. I tell you, whenever you are doing oscillations, that means simple harmonic oscillations, the primary condition is that there will be a restoring force, and restoring force, that means which tends to restore the particle, that means this projection, this is the particle we are interested in, to the mean position, and this restoring force must be proportional to the displacement. I hope you understand a little bit. This is an introductory thing to SHM. There are a lot of examples which we will handle it. I have actually a lab. I always use my laboratory instruments to teach the typical subjects. If you are interested, you can contact me for the JEE and NEET batch, and